Hey everyone, and welcome to part 2 of the fossil record overview. This can barely even start to crack the surface or the tip of the iceberg in terms of all that we actually know and have discovered about the fossil record. But a good question is, while you can make nice little trees like this where you demonstrate all of the creatures beyond a certain point have particular species, um, are there actual common ancestors that exist between these major groups? Um, so, for example, you could have some kind of eukaryotic common ancestor here, and on one of the branches you have you have a nervous system developing, and on the other one you don't. And on the one that you don't, those are sponges. They're up there, but all the others, everything beyond that point, on the bottom portion, has a um, let's see, can I draw on this? Let's see, how does that work? Pen. This region right here, of course, if you go down, all of these things have two embryonic cell layers in a nervous system, and then you actually have a simplification here where the placozoans, they actually lost their nervous system, and we can talk about how you could identify. Why wouldn't you put placozoans up here instead? Well, they would share all of, some characteristics here, but you can actually lose traits over time, of course. And then going on and so forth, everything beyond this point has bilateral symmetry along this axis. Three embryonic cell layers. The blastopore develops into an anus and deuterosomes here, and then protozomes. Here you have here, and then of course everything with a notochord falls into this little category. Now, of course, that's a nice story, but how could you do we actually have fossils connecting these? Because you could do this with anything. Just because you can do it doesn't mean this doesn't actually demonstrate that any of the gaps in between these are filled in. It's just that there are just some general structures that seem to be useful or required for certain types of life. Let's take a look at that. Well, let's look at the first mollusks, for example. This is found only in Cambrian era rock. This clearly looks like a mollusk, but it has gills, segmentation of gills, and muscles similar to its ancestors. And so there's no living mollusk that has such segmentation. It's really interesting. It's really sort of a halfway between mollusks and a halfway to worms. And you can do the same thing with fish. You see the development of various traits over time. You have the notochord, and then you see the development of a head. So at one point, fish didn't have heads, but they did afterwards, and then paired fins in the vertebrae, and then the fusiform body scale, so on and so forth, and you see just a development of things. But an interesting thing about this is this group in particular here. Here's a lancelet, and here's an acorn, quote-unquote, worm. So this is actually a species that exists today. Well, at least a variant of them. And so it's really interesting that you can have this branching. It's not as if the ancestor to lancelets that don't have this segmented or developed head in the same way that the species beyond it have. Um, um, but you don't have to have this particular organism becoming more and more complex over time. As a matter of fact, if you have a splitting of population groups, so some go this way and others go this way, then all of the characteristics that are gained by this lineage are not necessarily gained by this one. This one doesn't even have to gain them. And the lancelet, the modern ones, actually help us to learn about how a lot of genes that existed have simply been repurposed for new functions in modern fish and in other vertebrates. So that's really interesting. But the lancelet highlights something nice because there are such things they're kind of like called, quote, living fossils. It's really a misnomer. The vast majority of fossils, of course, are quite different from modern animals. That's important, but there are some notable exceptions, like a horseshoe crab. This is a category of fossils that they're kind of like in the slow lane in terms of evolution, but that really stems from a misconception. It's not surprising to see anything quite like this because animals don't have to become more and more complex over time. If they work well, if they can reproduce well, and their environment doesn't change a whole lot, then their particular um, body plan is going to work just fine. And it just so happens that many of these we find in the quote-unquote slow lane of evolution happen to live in environments that have been fairly constant. So, for example, horseshoe crabs have been, the shores to seas have been pretty much a staple on Earth for a really, really long time. And again, you know, that you could pause and reread some of these. I mean, if you have a niche that doesn't change, there's, you know, it's almost like, why fix what isn't broken? You could have slight changes to a population over time, but really, it's not about just becoming more complex. It's about what actually works well in that environment. You don't have to be more complex to be reproductively successful, and that's an example here. And so you have these types of living fossils, and they're really not surprising, but they're really more or less the norm. But even ancient horseshoe crabs are quite a bit different from modern ones, and so that's also significant. So anyways, what about coming out of the sea? So this is, of course, a famous topic, if you will. Tiktaalik would be one of the first. Here's another reconstruction of another creature here, where you see really a changing of traits over time, where you have some kind of more, here's an example of this paper on the left, going up here, you see a branching off at different points, really a changing, well, of course, of the eye sockets, nose, holes, so on and so forth. Also of the hands, up here you see a significant changing. From a more fin-like thing to a spreading out in the formation of various digits that you have forming. So you had a larger number of digits at first, then you see kind of a reduction of digits, and then you have, of course, living tetrapods. And of course, Tiktaalik, a remarkable fossil find that was actually predicted beforehand. So the question is, beforehand, if we see things like this, and then afterwards we see living tetrapods over here, how do you get from here to here? Well, there had to have been some kind of intermediate form within the geological strata. So if this one you're looking at, let's say you're looking at 400 million years ago, and then this one, let's say you're looking at 325 or so million years ago. So sometime in between those two time periods, and so that of course led to the discovery of Tiktaalik by Neil Shubin, a great story worth reading, and finding. And that's a remarkable thing. If this idea of common descent is true, then we should find these intermediate things, and we have an awful lot of them. And of course, there are lots of interesting discussions about where exactly to place Tiktaalik. So again, it would be wrong to conclude that Tiktaalik's in a transitional form, because it's really not. It's not as if this particular species was just suddenly becoming more land-like and then it evolved straight into that. That's not how evolution works. But of course, they would be related to one another. Tiktaalik very well could be some kind of sister taxa. We don't really know. We don't have a lot of fossils, but we do see a lot of fossils with intermediate traits. And so here's a famous or infamous example of Kirk Cameron saying, "But you've never seen a crocodile." And so this was a debate, does God exist? And Kirk Cameron said, you've never seen a crocodile. So this is a predatory duck. This is what many might actually think of, though, this impossible hybrid monster species. And so, of course, a question is does he think that evolutionists or, well, just scientists believe that in order for a duck to evolve, first there's a crocodile, and then it evolves a duck body, but keeps the crocodile head, and the head eventually becomes a duck head. And then since we've never found a crocodile, evolution must be false. And that's, I would hope that that's not the impression that any of us might have, but we do see a lot of intermediate forms where we see some kind of fossil beforehand, and then we see kind of a mixture of traits, and then we see some of those traits disappearing. We're going to go through an example a little bit later, looking at dinosaurs in particular. But it turns out, have you ever seen a frogamander? Because frogs and salamanders should have split approximately 250 million years ago. So could we ever find a frogamander type of ancestral species? Well, it turns out, yeah, here's an example of an actual species. There's this, I wouldn't use the word proves in this caption, but certainly it provides evidence that modern amphibians, frogs, and salamanders did actually come from a common ancestor, that it shares like intermediate traits of all three of those modern groups. And it just so happens to live in the right area, which it should. Here's another example where this is what is this? Is it amphibian or a reptile? Well, usually we could just simply judge this, what kind of eggs they lay, but we don't have any eggs, just this particular fossil. And so this is a really interesting find, and it becomes increasingly difficult to fit fossils into modern categories. Why? Because they have a mixture of traits, and this is really also hard to do with different members of the Homo genus as well, as we'll talk about next week. And so what was this species in particular? Ultimately, though, it was maybe a reptilian-like amphibian or an amphibian-like reptile. We don't know. And so it tends to have a mixture of particular characteristics as we go back in time. And then, funny enough, we actually did find the crocoduck anyways. Here is a predatory aquatic reptile. So here's Spinosaurus. This is the only dinosaur that shows aquatic adaptations, a nose opening far back in the skull. That was as of 2014, so maybe that's been updated since then. But certainly would have been a terrifying thing to actually find. And this is something we've seen particular adaptations as well. In animals that return to the sea, such as we see similar types of convergent evolution in this particular dinosaur compared to other dinosaurs, as we see in the transitions from whales to their most recent land walking ancestors. So it's really interesting. Then turtles, here's a nice example of some ancestral turtles. So here's a toothed turtle, and modern turtles have lost their teeth, and they have half a shell on its belly but not on its back. And it retains the reptilian teeth, which all modern turtles have since lost. And here's perhaps even more older primitive type of turtle, that you have flat, wide ribs starting to form some kind of shape, and the vertebrae are fairly similar to some modern types of turtles, but it doesn't actually have a hardened turtle shell. But this is found in the Middle Permian era. And then, of course, dinosaurs, you see, you can organize them into these nice cladograms where basically you can just organize them based upon the particular traits that they have. So if you wanted to see a nice review of horned dinosaurs, you could go ahead and see that reference there at the bottom. It's a book. You could do this with sauropods as well. What about reptiles to mammals? That's an interesting one, where you would have some kind of reptilian dinosaur-like thing, I guess. At least that's the main dominant form of reptiles in the era before the mammals really start to rise. And so Dimetrodon actually would have been one of the dinosaurs that would have been closest to modern mammals, if you will. And so here's an example of a lot of different skulls, and you see slight changes to these skulls over time. Here's a particularly relevant one, Diarthronagus, that has pretty much a mixture, or at least similar structures to reptilian-like joints with mammalian-like ones in terms of the structure, and so that's really interesting. Here's elephant feet. For example, we see small changes to elephant feet over time in different eras. So the black bars there, these ones in particular, those represent the time periods in which we see these particular species. So here's an example of some different species, and we see in a temporal type of sequence slight changes to the foot bone over time, arriving at a more modern elephant type of structure. You also see the same thing with tusks. You see the same thing with various traits that species have over time. So this would have been some kind of common ancestor. Then you see the elongation of the trunk here, and then the development of the tusks upward and curved. And then you see a transition into eating plants and all the species after this. And then you see an enlargement of the ears, finally leading to modern elephants. So you see these slight changes over time within the fossil record. And here's an example of aiming to piece that all together in a little bit more detail. We have all of these different types of species here, and so on and so forth. You could read the caption if you want. You can go ahead and pause that. Here's giraffes. So basically you have a short necked a giraffe, and then they just stretch their neck, and then they just got bigger and bigger and bigger. Just kidding, that's Lamarckian evolution. Now here's an example of the lengthening of some bones in particular in the neck in different species time-wise. So here's an age range here in particular. So here this is representing the species in this time range, so on and so forth. Here's an interesting, truly really long neck giraffes are fairly recent in the fossil record, about 7.5 million years ago. But we do see very important changes, small changes in different parts of the neck that lead to very drastic changes in terms of the overall neck size. But you see some very key features linking this modern neck bone to more ancient ones. You see a small change over time, really a thinning of this, an elongation of it, and some other tweaks from so on and so forth. So that's really important. Here's an example of some other closely related species to the modern giraffe. Here's an example of looking at some teeth and some other body types of structures, odd toad-hoofed mammals in the fossil record, and you see a lot of just slight changes really from species to species. If you will, in the fossil record, you can see just slight changes in the teeth over. So let's also look at dinosaurs and birds. You have a modern chicken here on the top versus an early protosaurus, well, one of the first dinosaurs. We really have a long way to go if we want to establish. What are some of the things, just looking at the fossil, that we would need to establish? Well, you see walking on 4 limbs, walking on 2 limbs. Each limb, these limbs are different. They are terminated with several fingers or toes. The tail much longer than this, really short, and teeth. There's no teeth here. So there's a lot of different changes. This is not a lot of changes, if you will, but do we actually have fossils that could potentially link these together? Well, it turns out you can do this looking at small changes in the fossil record over time. So, of course, that was Protosaurus here, and a short time later we have Asilosaurus appearing, walking on 4 limbs still, but having shorter arms. And what would that be indicative of? Really an increased ability to walk or stand on your hind limbs. And then sometime later we see Marsuchus. Is that how you say that? Marsuchus. Seems about right. Very, reptilian in form, very dinosaur-like, but notably bipedal. And so this is one of the first bipedal types of dinosaurs that we see, and really some small changes in the skull and similar tail type of structure as well, but just a continual shortening of the arms. Now, of course, this is not just a single kind. There are all kinds of other dinosaurs that came about. Here are some of the earliest true dinosaurs, if you will, popping up about 5 million years after Marsuchus. A typical trait is this particular hip socket with a hole in it, and there's also a notable change in the fingers. Modern birds don't have fingers, but their wing bones terminate with looks like remnants of 3 fingers. And so here's an interesting thing we start to see. So, for example, the previous one, it was bipedal very clearly. But in this one we see still bipedal, but then we see a change to the finger bones. Here's another one where the pinkies almost practically lost. The toes have reduced digits in number, if you will. Earlier dinosaurs had 5 toes. This one in particular, Coelophysis, had only 4, with a tiny remnant high up on the foot. And birds have 4 toes, 3 in the front and 1 in the back. So this is really interesting. We see kind of a prototype of that particular thing in some of the earliest dinosaurs, but really small changes from the dinosaurs that came before this. Here's Spinosaurus, 2 million years later, only 3 fingers, lost the ring finger altogether, and dinosaur marriage obviously became a thing of the past, and that is why God had to wipe them out, because they no longer respected the covenant of marriage. And so here's Archaeopteryx. Here's an interesting thing, where we began to see more bird-like features coming, and Archaeopteryx is one of the first and has a particularly striking mix. The appearance of feathers was one of the most significant things that is notable in this particular specimen. But an interesting thing about these feathers, they don't appear to be for the purpose of flight, but for regulating body heat. And here's a bunch of other feathered dinosaurs that we now have. Archaeopteryx certainly is not the only one, and so certainly dinosaurs had feathers, and they developed them at some point. Some particular important things about Archaeopteryx is that it had a wishbone. That type of fusion that it has with the furcula is also present in other carnivorous dinosaurs like Allosaurus and Velociraptor. But at the same time, how is it not like birds? Well, it still had 3 fingers along with claws on its hand, a long bony tail, and teeth, which modern birds markedly do not have. Here's Sonorous, another 15 million years later. Finally, we see a reduction in the tail structure and some fusion for feather attachment. And then you see the sternum also becoming increasingly keeled. That, of course, would have allowed for more powerful flight muscles to be attached, but it still has teeth and distinct clawed fingers. And then 40 million years later, we see Ichthyornis. Many limb bones have essentially become fused. This is clearly a skeleton well adapted for flight, but it still had teeth. And then, interestingly enough, there's like a primitive beak that appears to be forming in this particular fossil. And then on the bottom here is almost like a prototype penguin type of thing. We see various species like this starting to appear and arise after the disappearance of many of the other dinosaur species in particular. But we see really what is the difference between these two in particular? Is there a really big difference between them? And the answer is no, there's not. There's not a very big difference between these two particular specimens. We find that in particular. And so it's a really interesting thing. This is just where we're going to end for now. Short and sweet, if you will. Really doesn't do full justice to this, but we do see over a 200 million year period. We see, of course, the advent of feathers and wings in particular. We see the advent of bipedalism, reduction of fingers and toes, reduction of the tail, and finally loss of teeth. And so here's an example of an increase of feathers in various specimens over time. And so on and so forth. And here's some examples of the skeletal morphology changes over time. Here's three in particular that are focused on in this middle region here, if you will. And so birds are in fact dinosaurs. You don't actually shed in the same sense that humans are. Well, we're primates. We are, and primates are also mammals, and so on and so forth. Mammals are also tetrapods. Humans are all of those things, and that's how this type of classification would work. But anyways, birds are dinosaurs, and if you needed any more proof that there is no direction to evolution, you might say you've gone from a T-Rex to a chicken. If there's any teleology built into that, shame on you for giving us chickens. Well, actually, chickens are wonderful. Probably better than having a bunch of dinosaurs running around. So actually, we should be thankful that the dinosaurs did actually go extinct, thanks to, well, a large number of extinction events. There was, of course, volcanic activity in in Asia in different parts, and then, of course, the big asteroid that hit in Mexico. Modern-day Mexico. So anyways, that's it for now. We're going to talk about genetics next time and also look at the cetacean fossil record a little bit more.